Welcome to SKEW-T Log P101. My name is Scott Dennstaedt, and I'm a CFI and former National Weather Service research meteorologist, and I'm also EAA's weather subject matter expert. And I've co-authored a book called Pilot Weather from Solo to the Airlines, co-authored with Doug Morris, who is a Boeing 787 captain for Air Canada. And there's my website, pilotweatherbook.com. So today we're going to talk about why use a SKEW-T Log P diagram. What's the purpose? Why use this diagram in your pre-flight briefing? And next we're going to get into the components of a SKEW-T Log P diagram. Then we'll go through and talk about the input data sources that are used for the SKEW-T diagram. And again, we'll cover some of the various different lines on the SKEW-T diagram and talk about the base diagram itself, and then go into some application of how to determine stratiform cloud bases and tops, look at freezing level and icing, and at the end, if there's time, we'll have some questions and answers. So why the SKEW-T Log P diagram? Well, first, it provides you with a lot of good weather guidance to help you make those operational decisions prior to flight. And I think it really covers and increases your situational awareness, makes you more aware of what's going on, because it really fills in those gaps, and it confirms or even potentially contradicts other guidance you might be using. And second, to learn the diagram really requires you to learn the basic principles of weather. What causes icing, turbulence, thunderstorms? What causes that low-level wind shear or mountain waves? All those elements really provide an added advantage to learning this diagram. I actually use it as a canvas to teach weather. So when I'm teaching the pilot about the SKEW-T diagram, well, I'm actually teaching them all about weather. So one of the questions I get is, Scott, how long is it going to take me to learn how to use this diagram and become really proficient at it? Well, I generally say it's around 15 to 20 hours or so of dedicated training. I've done this with a number of pilots, and it's worked out real well. So over a period of 15 to 20 hours of dedicated one-on-one training, I've been able to do this online as well as in person. And I think overall, eventually, again, it takes a lot of practice, but eventually you get to the point of using it. It becomes natural to use it in your daily flight planning. So the other aspect of it, it can really provide you an understanding of how the environment is poised. Are you going to have a clear day like you see here on the left, or more of a cloudy, more of a convective day as you see on the right? It also will help you determine where maybe the bases and the tops of a stratiform cloud deck are located. And it also tells you a lot about icing. So it gives you the indication of the depth of an icing layer at any particular location. Really helpful. Especially during the wintertime where we see most of the icing incidents and accidents that occur. So this is a great tool to be able to drill down and determine what's happening from an icing perspective. And we'll talk about both those stratiform clouds and icing a little bit later. And I really love to use this tool more than anything else to explore and drill down on things like a severe pilot report for turbulence. So in this particular case, I was departing out of Roanoke, Virginia, and I noticed there was a pilot report for severe turbulence at between 10 and 11,000 feet. So I pulled up the RADIOSONDE observation and took a look at it, and sure enough, I could see that the winds were really interesting at that altitude. So the winds are 325 degrees at 15 knots, and they increased, but they changed direction to 150 degrees at 34 knots. So what you see here is kind of what essentially looks like a tumbleweed in the wind field. And that, along with a couple of other aspects of this sounding, you'll actually be able to really pinpoint and know that this was just a thin layer turbulence event. So let's first of all talk about what a SKEW-T diagram is not. So it's not the same as a profile view that you might see in some applications. Certainly there's some aspects of this that you'll see in terms of clouds and icing potential that certainly the SKEW-T diagram and this profile view will match, but there's a lot missing from this profile view that you'll see on a SKEW-T diagram. We'll talk a little bit about that in uncertainty later on in this program. Also, the SKEW-T diagram is really meant to be used as a drill down tool. It's really not to be used as to determine the big picture. Yes, you can get an indication of how the atmosphere is poised, whether it be cloudy or clear, but don't use it as that big picture kind of situation. It's really meant to be used as that drill down tool over a particular location. Also, the fact is that when you do your pre-flight planning, you really should be using what's called a funnel approach. You start with the big picture initially, and then you work your way down to the details. And the SKEW-T really provides more about what's happening in the details. And so we'd like to think about that as a point observation or a point forecast. So here's the SKEW-T diagram. We've put all the lines on, and we certainly have the temperature in red and the dew point temperature in blue, and then we have the winds here on the right. So this is a full SKEW-T diagram, which happens to be a radiosonde observation out of Dulles, Virginia. I get a lot of questions about where do I go to get the best SKEW-T diagrams. Well, my favorite source, it's been this way for about 20 years, is the rucksoundings.noaa.gov. Rucksoundings.noaa.gov is probably one of the best out there, and there's certainly other ones available, and you can certainly search for that on the internet. But this is the one I've been using, and really find that it's the easiest to use overall. Okay, so the SKEW-T diagram provides a plot of atmospheric data, specifically 3 key variables that include temperature, dew point, and wind, all plotted as a function of pressure or altitude. From these 3 variables of temperature, dew point, and wind, we can infer a lot of things. We can look at where the location of clouds, the bases and tops, icing potential, turbulence, convective potential, low-level wind shear, visibility, haze and fog, precipitation type, a whole lot more is available using the SKEW-T diagram. We're not going to be able to talk about all these topics here in this particular program. We're going to touch on a few of them, though. So from the standpoint of data sources, input sources, what are they? Well, there's really 2 basic sources. There's the radiosonde data, weather balloon, and there's the weather prediction models. So certainly we can look at the radiosonde data. It's not that it's bad data per se, but we're going to see how it may not be as useful to you. But when you're starting to look at the weather prediction models, they produce very similar data to the radiosonde, so we can actually plot that data in a very similar fashion on a SKEW-T diagram and look at what's going to happen in the future. And so the rucksoundings.noaa.gov site allows you to pick and choose these different sources. So the one that you're going to almost always use most of the time is the first selection here. This is the rapid refresh model. It's the operational model set up on a 40-kilometer grid. That's the OP40, and this is, we'll see in a little bit, this is probably the one that's going to make the most sense to you. It's going to provide you with the most highest resolution of time and space. The next, you'll see the global forecast system. So if you're flying outside the US or outside of North America, you'll probably want to using the global forecast system. Also, the global forecast system actually forecasts further out in the future in terms of time. And lastly, we talked about radiosonde observations, or RAOBs. Those are the weather balloons that we can pull in. So any of these 3 sources here provide you with good information for your flight. And so radiosondes, let's talk about those first, are launched twice a day at 23Z and 11Z, so morning and the evening time frame. But they're deemed valid at 0Z and 12Z. They can also be launched at any other time. For instance, if there's a landfalling hurricane, they may launch a bunch of weather balloons in the area that they really want to understand and drill down, and also provide more feedback to forecasting models about where the steering currents are. So you may see these launched more than twice a day, but routinely they're launched 2 times every day. And they provide actually very accurate data. There's sensors on board that provide you the temperature, the humidity, where you get the dew point, wind speed, wind direction, and pressure. All really, really good stuff. But the problem is they have really a poor spatial and temporal resolution. When you look at this, we know temporally it's only twice a day in most locations. So that's really not really useful. So if you're trying to make a flight at 21Z and you really can't go back to the 12Z radiosonde launch and really make it useful, it's not going to be useful to you. And certainly, as you can see here, they're spread all over all of the country, but in the end, they're really not close enough together to really help from that standpoint. So the spatial and temporal resolution is really not all that good. So now we turn to model analyses and forecast. The analysis is the initial condition of the forecast model. A forecast model is a computer program that predicts the weather. And you can see for North America, we have this rapid refresh model, which has a pretty large domain covering all of North America. And the predecessor to that was the rapid update cycle, and that's where the RUC comes from. When this program here from NOAA was first launched, that was the model of choice, the rapid update cycle. And you can see that was a lot smaller area. So they've actually improved by now using a much larger domain. And of course, with the GFS, you can actually do a world domain. So model soundings, you might also hear them termed as forecast soundings, are probably where you're going to want to spend most of your time. And it's pretty high resolution in time and space. The RAP, or the rapid refresh, is run hourly and produces hourly forecast with a lead time, with a forecast out to 39 hours. So that's 1 hour at a time out to 39 hours. And by the way, it gets updated every single hour with all brand new data. So the rapid refresh has a 13-kilometer resolution, but that's fitted on a 40-kilometer grid. That's the OP40 that we were looking at earlier. And that's probably, again, the one you're going to be using the most. And of course, as I said, the GFS, the Global Forecast System, has a world domain. So you can get pretty much an analysis, initial conditions of the model, and a forecast for any airport in the world using the GFS model. And in fact, here's a forecast for Ross Island in the Antarctica. So it's important to understand that when you ask for a forecast sounding, you're not actually getting it right here at the airport. Instead, you're getting it at some grid point that's around that particular airport. And so the tool, the rucsoundings.noaa.gov, finds the closest grid point to that, and that's what you get. So if you plot the sounding, you'll notice in the upper right, it'll tell you exactly where that is. And it's 6.1 nautical miles on the 169-degree radial, in this case from the Charlotte Douglas Airport. It's important to understand where that point is, because if that point was, let's say, over an ocean or lake or maybe even mountainous region, it might not be representative of what's exactly at the airport. So be careful when you look at exactly where that is in relationship to the airport. I want to mention two couple pet peeves that just drive me bananas, and that is I hear pilots say, "Oh, I didn't know there was a balloon launched at my airport." Well, most likely a balloon is not launched at your airport, but there's a model grid point near you, near that airport, like we just saw. So somebody shows them a SKEW-T diagram, and it's a SKEW-T diagram for their airport, and they immediately think it's a balloon launch, but it's not. It's probably they're looking at a forecast sounding, and in that particular case, again, it's at a grid point nearby the airport. The other one that really drives me nuts is SKEW-T forecasts are just an interpolation of the data from the balloons. That couldn't be further from the truth. Interpolation is something that if you have like a line that's a 9 and 11 and you interpolate at a 10 in the middle, that means that essentially you can never get a higher or lower number than 9 or 11. It has to be somewhere in between. Well, that's not really what happens in forecast models. A forecast model could actually, instead of showing a 10, it can actually show a 12. It actually can forecast a high in the middle. So that's the job of a forecast model. So a forecast model takes in a lot of data, including the radiosonde observations, which are really important to forecast models, but it's just a small portion of the overall data that's ingested in these models. And at that point, it's the rapid refreshes run every single hour to update it, taking all the new data in to produce a new forecast. So it's much better than just an interpolation from the weather balloons. All right, let's talk now about the base diagram itself. There are 6 different lines on the diagram. We're not going to be able to discuss all of those in this program. We'll be discussing at least 3 of those. So you can think of this as some sophisticated form of graph paper, and that little bullseye in the upper left, that's called a hodograph. Now that's not really of interest much to pilots. I get a lot of questions about it, but ultimately it's used by meteorologists, and again, it's not as useful to pilots for pre-flight planning. So first of all, let's take a look at one of the first lines that you need to understand, and these are the isotherms, or lines of constant temperature. And you can see those, they're skewed here at a 45-degree angle, hence the name SKEW-T, and it's in degrees Celsius. So we have the 40 degrees, 30 degrees, so each one of those lines are labeled accordingly. And so I've highlighted here 3 of those lines. So we have the 0-degree isotherm, the 10-degree, and the 20-degree isotherm. So the nice thing about skewing it to the right, when you plot a temperature and you plot a dew point on the diagram, they pretty much follow straight up into the diagram itself, so kind of straight up and down. It kind of saves real estate when you plot it. Plus it allows meteorologists and such, and pilots as well, to kind of pick out different features easily if you skew it to the right. The next one is pressure in millibars, and the high pressures are near the bottom of the chart and lower pressures are at the top. And so here are the isobars that are common that you might see, in this case 900, 800, 700 millibars. And you'll notice that in this particular situation, as you get higher up, these swaths of 100 millibars essentially gets further and further apart. And that's because the atmosphere is compressible on itself. And the simple fact is the lower layers here from like 8 to 900 get squashed more than the upper layers in terms of the weight of the atmosphere. And so that gives the atmosphere's pressure, the pressure drops exponentially, hence the term log P. So now you know why it's called a SKEW-T log P diagram. And the last one we're going to talk about is pressure altitude. I know there are a lot of folks out there, a lot of pilots that are millibar challenged. I am as well. And so pressure altitude is what you'll see on the right here. So it's a little bit easier for pilots to understand pressure altitude, and it's pretty close to mean sea level overall, so I wouldn't sweat the difference there. So this is showing the 5,000 foot, the 10,000 foot, and 15,000 foot levels. So that's a good reference. So if you don't want to use millibars, that's fine. You can use the pressure altitude in thousands of feet on the right. All right, so just a quick review. So we have our red squiggly line here, and that's the environmental temperature that's plotted from a radiosonde or possibly from a forecast model. And then we have our environmental dew point, that's the squiggly blue line there, again plotted from radiosonde observation, weather balloon launch, or potentially a model forecast sounding. And then we have our wind speed and direction. All right, so now let's switch to an emphasis of some application of finding bases and tops of stratus clouds. So let's first of all talk about different cloud types. Now, I like to separate cloud types into 2 basic things. I'm trying to keep the discussion here pretty easily, but I think it's important that we think about these 2 cloud types in this way when we're looking at SKEW-T diagrams. That includes convective cloud types and non-convective. I know most of you are probably thinking cirrus clouds and stratus clouds and cumulus clouds. I like to lump them into, from a SKEW-T standpoint, convective and non-convective. If you can put yourself in the frame of mind, this is going to be so much easier to use this diagram. So let's first of all talk about non-convective clouds. There are 2 basic non-convective cloud types, and that is stratus and nimbostratus. Now, stratus are those ground-hugging clouds that produce those poor visibility and low ceilings. Usually requires you to have a instrument rating and flying on an instrument flight plan when you're dealing with stratus clouds. Deeper stratus sometimes can produce a little bit of precipitation. So when the stratus clouds get 4, 5, 6,000 foot deep, sometimes you'll be producing a little bit of drizzle. They're typically sometimes very isolated, but they can also be pretty widespread. So typically we have this radiational cooling that occurs in the overnight hours or early morning hours. As the Earth radiates its heat, we get cooling at the surface, and that can produce these stratiform stratus clouds. But it can also be associated with large-scale weather systems such as warm fronts. Now, nimbostratus are typically very highly layered, and they're going to produce some kind of precip, whether it's rain or snow. They can extend all the way from the surface up to 30,000 feet, so they can be quite deep, but they tend to be highly layered, as you can see in this picture. They're usually associated with some kind of major weather system, usually warm or occluded fronts. All right, let's now switch our attention to convective clouds. There are three basic convective cloud types in my mind to think about, again, for using the SKEW-T diagram, and that is stratocumulus, cumulus, and cumulonimbus, or towering Q. Now, let's first of all talk about stratocumulus. We're going to look at a little more details later on with stratocumulus clouds. Now, the most common cloud type that occurs is likely a stratocumulus clouds, and they can occur anywhere in the world or any time of the year, essentially. They're rooted in the boundary layer. It means that they are there because they're close to the surface of the Earth. The surface of the Earth produces that. You have moisture and you have heating of the day that causes those stratocumulus clouds to occur. They're generally no more than a few thousand feet thick, maybe 500 feet, maybe 3,000 or 4,000 feet, but usually not more than that. And they cover large geographic areas. That's where the strato comes from. Like stratus can cover large areas, but the clouds themselves are a bit unstable inside, hence the cumuliform aspect of them. So this is stratocumulus. They have a quilted-like appearance when viewed from the top. If you've ever flown over a stratocumulus deck, you know exactly what they look like. They're kind of a quilted-like, lumpy kind of look, mashed potatoes look on top. And that's because they are highly capped by a temperature inversion, which kind of limits their growth. So they kind of look like this magic carpet over a long range. Sometimes stratocumulus can cover 1,000 miles or so, but that inversion is the signature that limits the growth of these clouds and keeps them kind of capped. Now, cumulus clouds come in a lot of different varieties. The fair weather cumulus is the most common. It's rarely overcast, and mostly it's broken to scattered. And of course, then there's cumulonimbus clouds. Those are the ones characterized by really strong updrafts and downdrafts. And I don't just like to think about thunderstorms per se. Any kind of deep moist convection like towering cumulus or congested cumulus are just as dangerous. All right, so in order to find the bases and tops of stratus, there's really one key approach here, and that is to look at what's called the dew point depression. That's simply the temperature dew point spread. So how far the temperature and dew point are apart gives you the dew point depression. So you're looking for a small dew point depression. But it's all about quantifying uncertainty. And that is, the smaller the dew point depression, the more likely that you're having clouds at that particular altitude. So again, you're looking for small temperature dew point spreads, and that gives you an indication that there's a possibility of clouds at that altitude. And this really works pretty well for warm stratiform clouds. Once you get to about -10 Celsius and colder, not so much so. So what happens if the temperature and dew point are large? The temperature dew point spread are large, large dew point depression. No clouds? Well, maybe not. You have to also think about that other cloud type we talked about. We said there's two forms of cloud types. That's non-convective, stratiform, and then you have your convective clouds. So it could be, in this particular case, that it could be a convective cloud that could be forming and not necessarily a stratiform cloud. So again, we're looking at large temperature dew point spreads. That convective cloud is basically produced through unstable air rising, expanding and cooling until it saturates. So it's not like the temperature dew point coming together like you see with saturated conditions in a stratus cloud. Instead, the air has to rise, expand, and cool. And when inside that rising air, when the temperature and dew point reach saturation, is when you'll get the base of that cumuliform cloud. But around that cloud, when you look at the cloud itself, you may find out that in the blue sky around the cloud, it may actually be quite dry. And so forecast models can't possibly predict every single cloud. Certainly, it would not be able to predict this cloud that you're looking at here. But if you were looking at, let's say, a radiosonde observation that went up through that cloud, certainly it would capture it. But if it was launched, let's say half a mile either side of this cloud, it wouldn't have picked that up. So imagine flying into this cloud. The temperature and dew point will be much further apart. When you hit the cloud itself, the temperature and dew point would come together, become saturated. Then when you pop out on the other side of that cloud, the temperature and dew point would be further apart. Essentially, what you think about that, the model soundings themselves, the forecast models, basically predict the environment that this cloud can grow within. So it really predicts the blue sky around the cloud, not the cloud itself. So in those cases, you can actually have a pretty significant temperature dew point spread, 6, 8, 10 degrees, but still have the possibility of these cumuliform cloud types. So again, the model basically just shows how the atmosphere is poised to build or grow these clouds. So in the case of stratus clouds, though, you're looking for that small dew point depression. Where are the temperature and dew point equal or nearly so? So if you see a dew point depression of 0, you've got a lot of confidence that you're probably dealing with clouds at that altitude. You can see that here on the SKEW-T. You see you've got a case where we have the temperature and dew point being equal. So there's a really good chance that we're at that particular altitude that we are actually in a cloud. But you have to really understand uncertainty. Finding the bases and tops really all is about quantifying that uncertainty. So when you look at this depiction here, it looks like a binary condition. You're either in the cloud or you're not, but models can't really predict this to the exact measure that most pilots would want to see. So again, let's talk about quantifying that uncertainty. So if you're looking at either one of these depictions on the left or right, you can see kind of a big difference. So on the right side, the air above the clouds is pretty dry overall, but when you look on the left, it's actually got some scud above the clouds, and you can see two different situations. So the one on the right may be more crystal clear, and you can have a lot more certainty that you're on top when you're looking at the temperature dew point spread, but it's very common to be 1,000 feet above the clouds and still have the temperature and dew point be pretty close together, giving you an impression there could be cloud at that altitude. So my general philosophy is to look at it from an uncertainty standpoint. So in this particular scenario, I'm very certain that at, let's say, 3,000 feet, I'm probably in the clouds because the temperature and dew point are exact. Now, in this particular situation, I know I'm really above the clouds here in this green area because the temperature and dew point everywhere in this green area is pretty far apart. So I have a lot of certainty I'm above the clouds in this point. But what about as you get closer and closer to that point where the temperature and dew point or spread is 0? There's a little bit of area of uncertainty here. And so this gives me a little bit of pause to think, well, maybe at 5,000, 6,000 feet, I may not be above the cloud tops. And certainly maybe about when I get to 7,000 feet, I got a lot more confidence that I'll be above those clouds. So if you're flying in that general altitude, you might actually not be above the cloud tops. So this is the area of uncertainty that we were talking about. And it becomes even more difficult when you're dealing with, like, say, a NIMBOSTRATUS deck. In this case, you can clearly see that we've got some temperature and dew point spread is of 0 in this case. So the dew point depression is 0. And so there's a pretty good chance that I'm in clouds at those altitudes here at 10,000 feet, at 5,000 feet, or I'm in some kind of precipitation because these are, again, a nimbostratus kind of cloud depiction. But again, if you look at this, I can be really certain at 30,000 feet I'm probably above the tops. But where are the tops here? It's really hard to tell. The temperature and dew point come close together. And most likely this is a situation where we're dealing with a potential glaciated situation, so that in this situation, -10 is right about here. When you start getting into the -12, -15, -20, we start to trend towards a glaciated condition, and the dew point temperature is just not a great way to measure saturation. A frost point would be better, but we have displayed here as the dew point, so it's not uncommon to have the temperature and dew point be kind of far apart, 2, 3, 4 degrees, but still have saturated conditions. But the area of uncertainty here is pretty significant over a really long range of altitudes. So let's go back to that profile view that so many pilots like. You really don't see that uncertainty here. Yeah, certainly it shows you you've got some clouds and some icing potential, but it doesn't tell you how much uncertainty. So this particular application made some assumptions and put those clouds there. You don't know what those assumptions are. You don't know what the lapse rates are based on this. So there's a lot of stuff missing from these profile views. They're great. They provide you some information, but I like to know, what assumptions are being made so I can know exactly where that uncertainty is. And certainly the SKEW-T diagram can provide that, whereas this cannot. So the first one, and we talked about, are warm stratus clouds, and are clouds essentially that are above, in terms of warmer than -10 Celsius. And so it's pretty easy to pick out where those clouds would be located. But once again, we have that area of uncertainty. We're not really sure. Certainly at 15,000 feet, we're probably not in any clouds. Certainly at 3,000 feet, we are. But where are those tops? Really hard to say for sure. You move this over just by a couple degrees and you're really in that area of uncertainty. And of course, deeper, more stable clouds like these NIMBOSTRATUS clouds, again, you'll probably have precipitation anytime you see a situation where you have saturated conditions over 10,000, 12, 15,000 foot depths. You're most likely going to be dealing with a precipitation event. But again, where are those tops? It's really hard to pick that out and be absolutely certain because of this situation. So let's go back again and talk a little bit about stratocumulus clouds, because they have a distinct signature on the SKEW-T diagram. They occur just about anywhere in the world, and pretty much any time of the day or night. And they're rooted in that boundary layer. They're really close to the surface. Usually we're talking about a couple thousand feet to maybe 5,000 feet for the basis, but they generally are close to the ground. Only typically a few thousand feet thick, so if you've ever flown through a stratocumulus deck, normally you're in and out of those pretty quickly. And they have that quilted-like look when viewed from above, but they have this distinct signature on a SKEW-T that I want to point out. So here's the situation. So you have unstable conditions. So this is a lapse rate of about 3 degrees per 1,000 feet here, and that's the dry adiabatic lapse rate, which is this other reference line that you see. The blue line that you see here is a reference line for the dry adiabatic lapse rate, or 3 degrees. So this is very unstable at this point. And then you see the temperature and dew point are really close together, implying the possibility of clouds. And then you see the sharp right turn of the temperature. There's your temperature inversion, which basically caps those clouds. So that strong temperature inversion with the unstable air below is a signature for stratocumulus clouds. And that really basically gives the stratocumulus deck that kind of flat look to them, but lumpy appearances. That warm air, unstable air is bubbling up, sort of like boiling of water, bubbling up to the top, and then you see the lumpy appearance on top of those clouds. All right, let's talk lastly about airframe icing. Now we know that liquid doesn't necessarily always freeze at temperature below 0 degrees Celsius. That would be really great if it did, but unfortunately it does not, and that results in supercooled liquid water. So water drops must have some kind of nucleation event in order to freeze. You have to have some kind of dirt particle we call an ice nuclei, very microscopic, and those are kind of rare and don't activate until the temperature reaches about -12 Celsius or colder. Once we get to that temperature, then we can then start to produce more ice crystals and not have supercooled liquid water present. So ice accretion depends on 3 different things. It depends on drop size, liquid water content, and we're only going to be able to talk about one of those, and that is temperature. So those 3 are responsible for the icing airframe characteristics. So icing factors basically are associated with, in terms of temperatures, that we can have ice, have supercooled liquid water at temperatures from 0 degrees Celsius all the way down to -40. Once you get colder than -40, you get what's called homogeneous freezing, and that essentially freezes no matter how pristine the drop is, it will freeze. And most of the the crystallization that occurs is due to that nucleation event called heterogeneous freezing. So in this particular scenario, what we see here is a study that was done by the folks at NCAR in Boulder. And you see here that we have the RUC forecast temperatures that are shown here in degrees Celsius. And the RUC model, Rapid Update Cycle models, allows them to take a bunch of pilot reports, find out their location and altitude, and at that point they can plot where in the temperature regime those pilot reports occurred. And you notice that most of the icing occurs in that 0 to about minus 15 Celsius range. So that 0 to minus 15 is where we see the most, with kind of a peak right around, let's say, minus 7, minus 6. So essentially, if you're in that temperature regime, you're more likely to get airframe ice if you're in those saturated conditions. And that tends to taper off pretty abruptly and pretty quickly, but you can still see there's a lot of icing reports at those colder temperatures. And when you get to about minus 25 and colder, icing is definitely a lot less likely unless you're in convection. So anytime you're in any kind of deep moist convection, such as thunderstorms, hopefully you're not there because of the turbulence, but we can find in many cases there's not unusual to find temperature icing or supercooled liquid water down to temperatures as cold as minus 30. In fact, one of the coldest ever recorded by an instrument aircraft was from Environment Canada, which recorded a minus 37.5 degrees Celsius, and that was actually in some deep moist convection. If there's anything that you take from this program, I want you to be able to find the freezing level on this chart. So if there's anything that you take away, this is the one thing I want you to do. So we call this, finding the freezing level, or the melting level if you want to be more accurate. So that's pretty easy to do, and that is you locate the 0 degree isotherm. You see that here because I highlight it. And what you want to do at that point is find out where the temperature, the environmental temperature, the squiggly red line, essentially crosses the 0 degree isotherm, and you can read that off around 10,000 feet. So it's pretty easy, pretty quick to find that. Now, I have noticed that some instructors are teaching pilots, in some cases, just use the standard lapse rate. Find the temperature at the surface, and then use the standard lapse rate 2 degrees Celsius per 1,000 feet. So if you did that in this case, essentially the blue line here is the 3 degrees, so it's probably a little bit less than that. So you take the surface temperature and you go up to 2 degrees Celsius, and you probably are looking at 6,000 or 7,000 foot based on that kind of estimate. And we can see the actual freezing level is more at 10,000 feet. So don't use that rule of thumb to use the standard lapse rate. That only works when the environment has a standard lapse rate in it, and most of the time it does not. So what you want to be able to do in order to look for icing conditions, those are conditions that you would likely run into supercooled liquid water. You're looking the same thing as you're looking for clouds. You're looking for that small temperature dew point spread, the small dew point depressions in the warmer subfreezing temperatures. Remember, we said 0 to minus 15 is where we generally see most of the icing occur. So that's where you want to look in terms of the temperature regime. So it's very similar to, again, looking for where you have clouds. You find that freezing level, wherever that happens to be, and what you're trying to do is find out where there are saturated conditions at temperatures below freezing. So in this case, the temperature below this point is all above freezing, and then you cross over the 0 degree isotherm. So anywhere from, let's say, from about 7,000 feet up to maybe 11 or 12, you've got the possibility of icing conditions in that altitude range. And then also you have the possibility of finding multiple freezing levels. And this is real important because multiple freezing levels can lead to a freezing rain event. So you can see in this case, I saw that there was a freezing rain situation out of Charleston, South Carolina, with a surface temperature of -1. So I pulled up the SKEW-T Log P diagram, in this case a radiosonde. R stands for radiosonde observation. And then you can see that there are definitely two freezing levels. So here's the 0 degree isotherm, and then there's the actual two freezing levels where it crosses over, the temperature crosses over it. So if you are at an altitude between these two, you are in temperatures above freezing and there's no icing threat. But you know if it's precipitating in any way, and you've got this saturated, fairly large saturated, all the way from around, let's say 10,000 feet, nearly saturated all the way down to the surface, you've got the possibility of freezing rain in the area below this. So the temperatures are all below freezing. If it's precipitating and the temperatures are below freezing, you've got likely a chance for freezing rain. And last but not least, is it too cold for icing? Is it ever too cold for icing? The answer is yes. Once you get to a temperature, about minus 20, 25, 30, you're really in those regimes where you're dealing with glaciated clouds. So if you have a surface temperature of minus 20, most likely the atmosphere above that is way colder. I always look at that as a surface temperature minus 20. You're probably going to be looking at glaciated clouds, which means all ice crystals in the clouds. And so you could fly through that cloud without having any certified ice protection system and have no fear of accreting any ice. All right, that's all, folks. So we'll go ahead and take some questions. And here's my website if you were interested in purchasing from pilot weather from solo to the airlines. We have a soft cover and ebook now available for purchase at pilotweatherbook.com. And there's my email address if you want to email me directly.